All right, so the assignment that I'm going to give you today out of chapter 30, I'm just going to give you the institute. So the significance of this, out of all the assignments, labs, everything that this is the last time I will say, does anyone have any questions on the assignment?
So I think because this is such a big moment, we should go through every single.
Yeah, we should.
Yeah. Because it's not even that long.
We can do this.
You like
Yes.
conversation?
Okay, just give me the answers.
So,
Bert, I don't get it.
Yeah, this one might be.
let's start
Just do it right
the
now.
important part of this in terms of that first question. So on that first question, so it's the answer short, but if asked to, the is completely transparent, why doesn't the answer absorb orange and red wavelengths? So here's the story, and this is true of this glass, whatever it is. So, and thank God our atmosphere is this way. So if you look at our atmosphere, we have a bunch of oxygen, we have a bunch of nitrogen molecules. So the cool part about that is in terms of photons, is that these photons go through it, but they don't interact with it, okay? Which is the same thing with glass. Now, they technically interact with glass a little bit because they slow down, you can get into index of refraction. But for the most part, they pass right through, okay? And so that's why, and the only reason that happens is because of the fact that the photons aren't capable of exciting any electrons. So the reason that you can't see through meat, okay, or a door or anything that's solid, is because of the fact that those photons get absorbed, reflected, whatever, and they don't pass right through. So the good thing about our atmosphere, being the structure of oxygen and nitrogen, is that they allow sunlight to pass through. That's a cool thing. If oxygen and nitrogen absorbed sunlight, it would be darkness, okay? Now, we do have an atmosphere that conveniently absorbs a lot of ultraviolet light. The upper parts of our atmosphere absorb a lot of ultraviolet light, which is a good thing. Otherwise, it's going to pass through and end up in us. But that's one of the hazards in outer space, is that you don't have an atmosphere to filter out that UV light. So things out in outer space are bombarded with a lot more things than we are, because we have, in effect, have like the safety blanket around us. Okay.
What about infrared?
Infrared, that's a longer wavelength. That really isn't that big a deal. Okay. All right. So on question number 2, one the same element, a fixed element X, explain why they are different. So here's the difference between emission spectrums and absorption spectrums. So absorption spectrums only go from the ground level. Okay? So, like, let's say, for example, you could hear, if you want to call that n equals 1, and then you have another level of n equals 2, n equals 3, and then n equals 4. Okay, so you have these hypothetical energy levels. So what's cool about this, and this is what became counterintuitive to when they began to study the structure of the atom. And once again, you kind of have to view this through the timeline that says, oh, hey, we found this incredibly dense small nucleus, and you can have the electrons, and they'll go, oh, the electrons should be able to exist at any level or any amount of energy, and they couldn't. They only exist at certain energy levels, which is why you get emission spectrum with distinct bands of light. So, in terms of an absorption spectrum, you're going to bombard this thing with purple light and with red light and all of these different colors. And what's going to happen is that you're only going to absorb these electrons as they move from the ground state up. So this is why on that absorption spectrum, you have, it'll absorb the energy to move up to 1. It'll move to here. It'll move up to there. So in terms of an absorption spectrum, you would have, it looked like this continuous band of, like the full spectrum of light. And you would have gaps where it had basically soaked in that energy to move that electron from the ground state up. Okay? So you would have the entire spectrum, and then you would have gaps where it absorbed that energy to make that transition state. It would be continuous except for that. Now, on the emission spectrum, so the emission spectrum is going to be what's going to happen when they come back down and they, oddly enough, emit light, hence the term emission spectrum, radical concept. So, on the way down, obviously, you can have it where it goes from n equals 1 back down to that ground state. So on the emission spectrum, that would be one possible light that you can see. You could see it from n equals 2, that's the second one, from n equals 3, boom, down like that. So in terms of an emission spectrum, you would have those same number of lines. If emission spectrums work just like absorption spectrums, they would be the exact same. Couldn't tell the difference between the two of them other than they're like negatives of each other. But on the way down, you can stop in between. So on the way down, you could go from n equals 4 down to n equals 3. You could go from n equals 3 down to n equals 2. So on the way down on the emission spectrum, this is why you have more lines in the emission spectrum than you do in an absorption spectrum. So the general rule is that every line that's in an absorption spectrum is in the emission spectrum, but not every line that's in the emission spectrum is going to be in an absorption spectrum. Elliot.
So for like n equals 4, does that always have the same energy, or will it differ?
No, this is just a hypothetical. So n equals 4 in a sodium atom might be different than n equals 4 in a rubidium atom. Okay? So those vary because then you can get in like sp2, sp3. So what you might get, but here's what is going to be true. It's a good question. So if you see like a particular frequency of red light, you know that no matter what happened, no matter what that transition is, that change in energy had to be the same. Now, it might be a transition in one atom, that might be from n equals 4 to n equals 3. On another atom, it might be from n equals 2 down to n equals 1. But when you see that particular color, you know that that only happens with that distinct amount of energy. Okay? That makes sense? Okay. So, when you get to question number 4, can nuclei of the same element have different values of Z? So you got to know what Z is. So, is Z the atomic number or is Z the mass number? Z is the atomic number. Okay? A is the mass number. Now you would think that they would make A the atomic number. That would make sense. There's certain things about science that just always bug me. Okay? This is one of them. It's like, why didn't you let A be the atomic number?
Why is it Z? Why not him?
I don't know.
Why not
This is-
like-
That's the way it is. Okay. Now, the one way that you can justify this somewhat, okay, is let's say that you get carbon 14-6, okay? So here's the one way that you can somewhat justify it, is that you have the A on the top, and then you have Z on the bottom.
A to Z.
And it goes A to Z. That's kind of the one wonky way that you can kind of make sense of it. But
No, they don't.
hey, again, don't kill the messenger. I'm just telling you. I'm just telling you. Okay. So let's talk about problem. Question number 7. So. Question 7. So on question 7, the N equals 3 state of hydrogen is negative 1.15 electron volts. So this gets a little bit wonky in terms of how they define these systems. So on question number 7, what is it? It doesn't make any difference. It's a negative 1. So you have E3 equals negative 1.51 electron volts. And it's weird, sometimes, depending upon the author and how they handle this, some of them get real uptight about positive and negative signs on here. And even the AP test itself, sometimes they get real picky about this, and sometimes they don't. So here's the basic idea of why this thing is listed as a negative value. Was that, and it has to do with this concept of infinity. We talked about that when we were talking about electrical potential energy. And we said, imagine that you have an electron or a proton that's infinitely far apart, and then you bring them together. And so if you have like an electron and a proton, and they're infinitely far apart, then to keep them from going together, because they're attracted, you kind of have to keep them from getting together. Whereas if it's 2 electrons that are infinitely far apart, you would have to push them together, and then you're building up. And so it's the same kind of idea when you have a negative value. So here's the nucleus of a hydrogen atom, typically just a single proton. Okay? Sometimes you have a neutron on there, but 99.9% of the time just a proton. And so technically what they're saying is that this is a negative value. So here's this electron in a certain energy state. And the reason that it's negative is that if this electron was infinitely far apart, and he's basically being attracted to a proton because they're oppositely charged. So this electron wants to end up in the state because it's attracted to it. So because of the fact that it's infinitely far apart and it wants to go towards the proton, you have to like push it in the opposite direction that it wants to go, right? And so because you're applying a force in the opposite direction that it wants to go, because that's a negative value and that's a positive value, that's why it's defined as a negative value. Yes?
Well, when I went through the textbook, it said that it's negative because UE decreases faster. Like as an electron gets closer, UE decreases faster than the kinetic energy increases. Is that also
It's a weird way to express it, but yeah, that works. Okay. And so then when you get to 7, what is the physical significance of the specific number 1.51 electron volts? So for those of you that have just got done with AP chemistry, we talked about first ionization energy. This is how much energy that it would take that you would have to give that electron to make it go back infinitely far away.
So can I say that the energy takes to create?
Huh?
Can I say the energy takes to create?
Perfect. Yeah.
Can I say the energy is to pull it out?
To what? Completely. Okay. So on problem number 1, okay, and this is the visible spectrum of hydrogen. Determine the Balmer formula N and M for these wavelengths. What I find odd is that they rate this like a 1. Like this is like the easiest possible problem you could have. And it's really not. You got to do some math to get there. So on problem number 1, it's just kind of weird the way they do this. So you got lambda equals 91.1 nanometers divided by 1 over m squared minus 1 over n squared. Okay? And what they're trying to ask you to do, determine the Balmer formula N and M values for these wavelengths. So there's a couple of things that you can do. One option is that you can just kind of plug and chug the numbers in. Okay? And you can do that because if you look on that on figure 29, I gotta find it, give me a second. It's got the wavelengths of the visible lines 656 and 486 and 434 and 410. Okay? So a legitimate option here, and this is kind of what they did to find the Balmer series in the first place, is that it was kind of a guess and check kind of thing. The 91.1, there is no physical significance to the 91.1. It's just, they just figured out that it worked. Alyssa.
What is, okay, so 91.1 nanometers over what? 1 meter?
91.1 nanometers.
But it's over 1 over meter square minus 1 over.
No, that's 1 over m squared and n squared. M and n are the energy levels. That isn't meters squared.
Oh,
Okay? Those are the energy levels. Okay? Those are the energy levels. Okay? So, let me give you, if you go through the math, and like if you multiply across and then divide back, you get 1 over m squared minus 1 over n squared equals 91.1 over lambda. Okay? So I didn't do anything fancy. All I did is multiply it, move that over, and divide it back. So, like on that first one, where you have that wavelength of 656, you can take 91.1 nanometers and divide that by 656, and that equals n squared. And then if you multiply by that least common multiple of m squared and n squared, it's nothing big. You just get n squared minus m squared over n squared m squared, which sounds weird, equals this number, which is 0.139. And then to a certain extent, it just kind of becomes guess and check. But here's the story. These have to be whole numbers because they're energy levels. The beauty of it is you don't have to worry about fractions, okay? So to save you some hassle on that first one, m equals 2 and n equals 3. So the m value is always the smaller one, the n value is always the bigger one. So what we're saying is that imagine here's a nucleus, and your m values are going to be where these electrons start. So you can have m equals 1, you can have m equals 2. So in this situation, we're letting m equal 2. So, and that's going to be the same for all of these. So then your n value is where you boost that electron up to. Okay? So you can bust that up to n equals 3. So if you go through here and you put in these numbers and you let n equal 2 and n equals 3, and to a certain extent it is just kind of a guess and check kind of thing, but you know that you're limited on what you can have for your values of m and n. It isn't like you can't have infinite numbers like, oh, maybe n equals 1.37, maybe n equals 4.18, okay? They can only be whole numbers. Now, here's, I think, this was the ultimate game of guess and check when they were figuring these out, okay? It was literally, let's put in the numbers and see what matches up. Because they knew the wavelengths first. What they were trying to find was a mathematical way to describe what was happening to justify it. So in some ways, this is kind of like what Kepler did when Kepler found the 3 laws of planetary motion. Okay? He kind of said, hey, here's this law of harmony, ratio of periods over ratios of cubes of the radii, and he knew it worked. Why it worked? I didn't know. Took Newton to figure that out. So this is literally just a game of guessing check. So if you let n equal 2 and you go through here and you plug those numbers in, that generates a value of 0.139. So what you do on the other ones, and let me give you a hint, it just goes 3, 4, 5, and 6. Okay? So m's going to stay the same, n's going to go 3, 4, 5, 6. Now, here's the beauty or the significance of this. So if you look at those numbers, okay, on your wavelength, you're going from 656 to 486 to 47. So what's the trend in the wavelengths? Wavelengths are getting shorter. So what's happening to the frequency then? So you're increasing the frequency. So what's happening to the energy involved? It's getting more and more energetic. So what's happening is you're boosting these electrons into like a higher and higher energy state. So when they come back down, they have more energy, therefore you get a shorter wavelength, a higher frequency, and more energy. But what this did, and here's the bigger picture, is that, and this was the confusing part of this whole process, was that why did it work? Everybody thought like these electrons should be able to exist at any energy level. And that became the problem as to why didn't it? And then this is where the de Broglie wavelength came in a little bit later. De Broglie said, oh, these electrons have a wavelength. If you do that wavelength as a circle, hey, it has to be a multiple of that wavelength. And if you have the multiple of that wavelength, this is why the electron can only exist at certain energy levels. This is why you get the bright lines in the spectrum. Right? Now, on the test, which is going to be on Friday, okay? On the test on Friday, if I want you to do anything with this Balmer series at all, I will give you the equations. I will give you the value. Okay. Just understand the big picture of the Balmer series. Don't get hung up on it. I'm not going to expect you to know any really highly technical calculations. But the reason that I have you do this is that it's kind of one of the foundational things that happened in our understanding of the quantum side of physics. And like, oh, wow, this worked. How did it work? We guess and check. You did it enough times. Hey, it matched up. We got lucky. There you go. Okay. On question number 2, or problem number 2. So, called the Lyman series, calculate the wavelengths of the first 4 members of that series. Okay? So, those wavelengths on question number 2, the only difference is that you're using m equals 1 instead of m equals 2. So, you're going back to this lambda equaling 91.1 over 1 over m minus squared over 1 minus n squared. Okay? So this actually makes it a little bit easier because m is going to equal 1. So you really don't have to worry about that. It's just 1 minus the other one squared divided by 91.1. So what you should see is that those wavelengths should go from roughly about 120 down to about 95. So on problem number 2, this should go from around 120 down to about 95. There should be 4 of them. Okay? All right. On problem number 4. On the electrons, protons, and neutrons, do not randomly write down numbers and expect I'm going to know what they are. Okay? You might even consider like make a chart going, oh, here's the electrons, here's the protons, here's the neutrons. Okay, that's an option.
What if I just wrote the numbers, but after the numbers would be like P plus 0 with a slash through it, and then E minus.
Why you put 0 to the side? We already have a thing for that.
Well, no, this is like the slash goes. You got it.
That's cool. Here's the main thing. I just don't want you to write down numbers and think I'm going to know what they are.
If I have units, that's fine.
There really aren't units.
Well, not like units, but like simple.
I can live with that. I can live with that. On problem number 8. So in the diagram, what wavelengths appear in the atom's emission spectrum and the absorption spectrum. So on 8A, because it wants the emission spectrum, you should have three values, ranging from about 300 to about 800.
800, 300.
Oh, no, we're good, we're good, we're good.
300 and 800.
We're good, no, we're good.
Where's mine? 827, I guess.
Well, that kind of flipped you out.
I got 100 to like around mid 600.
Damn.
Oh no, bad.
8A, you said?
Yeah,
Bam.
Oh, that's really not.
but bad. What you have is bad.
So what do you mean by simple?
Oh,
You're actually a thinker.
8B should have two wavelengths, one around 300, one around 800.
Bro, this not
So I have 8. So you might make some
Oh,
think I'm just being
Let's
dumb.
speak loudly. He doesn't speak loudly.
wow. On 52, so 52 is a kind of a cool concept.
Oh, Ryan, you've done something.
So head-on collision, and this is what's called the point of closest approach. So 52 is a very good question that you are very likely to see a version of this on the test. Okay? So make sure that you understand 52. So here's the basic idea on 52. So closest approach, MEV. So start with this. So you have 6.24 MeV, which stands for what? Mega electron volts. It's just a measure of energy. Okay? And it's a lot because it's a mega electron volt. So you have 6.00 femtometers. Okay? So that's like the femto is the smallest potential like prefix that we have in measurements. Incredibly, 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 incredibly small distance. So basically what's happening is this. Here's this big nucleus of this particle. You're going to shoot this tiny little alpha particle at it, and it's going to hit and basically bounce back. Okay? And that 6 femtometers, it's hard for me to even begin to express just how small that distance is. But it would kind of be like this. Here's the best analogy that I can give you. That you have a cart with a plunger on it, and it's going to hit a wall. Okay? So the 6 femtometers would be the distance like the spring is compressed before it stops. So here's the bigger idea, okay? When this thing is moving in, it has a certain amount of energy. Technically, that's kinetic energy. You can say, hey, this is the energy that this thing has. Now, when it stops, what's going to happen to all of that kinetic energy? It's going to turn into ooey. If it was the spring, your kinetic energy would change into us. Okay? So ooey is the atomic level equivalent of us. Okay? That makes sense. So the only thing difference is that you don't have a spring constant. So you're going to set that amount of energy, make sure that you, I don't care what you do, but you got to do something, you got to make some conversion. Personally, when I worked this, I rolled that into joules. Okay? Just because joules is kind of a universal thing. So then you know ooey equals what?
K1
Q2
over R.
Or distance squared, same idea. So basically, here's what you have to watch. So on 52, is that the nucleus of an atom was what element, assuming the nucleus is heavy enough to remain stationary. And that was this is one of the things where Rutherford got lucky, is that he used gold. Gold has two unique abilities that worked in his favor. Number one, you can make what's called gold foil. Gold foil is basically one atom layer thick of gold foil. It's one of the very few elements that you can do this with.
Wait, seriously?
How do you make it?
Yeah. Literally, you just keep pounding it, and pounding it, and pounding it, and it gets thinner and thinner. Really high priced weddings, I've heard, never been to one, but they have like literally as gold foil over
Why are you
like.
biting your lip looking at?
Are you
Because
serious?
it's so thin.
You're weird.
Oh yeah.
Oh yeah, it's like, it's 1,000 times.
Bro,
thinner.
you're like actually weird.
Very. Why do people like gold foil so much?
It's just, it's cool, you can use it as decoration.
Is it cheap?
Oh no.
No.
What?
Is that the same like that gold flakes?
Yeah.
Like it's like flakes of gold.
Yeah, but this would be like the entire sheet.
Also, why is there a gold foil but not like iron foil?
Because iron isn't that malleable.
Very. Very.
What?
Can you digest gold?
What the hell? Is gold,
Yeah.
is gold the
Really?
foil of metal?
People put gold on food.
I know, but like I was thinking, I was
What?
like, is it like
People
actually
put gold on
digestible?
food.
Yeah.
Gold?
Like, is it like actually digestible? That's what
You
I'm
wanna
saying.
ask?
No, like,
You gotta ask these
like,
questions.
can you actually digest it? Like, does come out?
So here's, thank you AI. So the gold leaf is
Oh, we
typically
did our
0.1 to 0.2
dissection
micrometers thick, roughly 1/8,000th of a human hair.
How did you feel?
Damn. How does it even like hold together when you move
I was
it?
looking at it.
But that's the beauty of their atoms, is that they take them that thin, but they still have the ability
Yeah, they still
to hold
move.
it together.
Yeah, that was like
That's the cool part of
It
it.
smelled gross.
I know,
Okay.
it's like, it smells horrible.
Anyway, so your element on 52, you have to be careful when you're doing the charges because you have to understand that it's an alpha particle. Since it's an alpha particle, which is a helium nucleus,
Two.
yes. So when you're doing
Why
the
is it plus
Q's,
2?
one of the Q's is
That's
going
how
to be
it
2
is.
times 1.6. So basically, you solve for the other Q, and it should be, when you get done, a common metal that you might drink out of. So,
If you leave it in EV, you get like 14. And that's just like.
What is it? I don't know.
So which is,
Oh,
so you drink out of that.
Huh?
So you can just do like that.
Aluminium?
yeah, because that's the number of protons.
Okay.
Wait,
that makes
so-
sense.
Copper.
If I say UE equal to Q1,
Wait,
Q2
so you
over
get the
R
chart.
equal to Q delta V.
That's not D
Which is
squared,
2
by the way,
times
that's
1.2.
Oh.
That's not
No,
D squared.
that's
So if I
not-
say
Aluminium.
Q1 equals K Q1 over Q, I mean Q1
That
plus
one is
Q2
what?
over R
If you
equals
leave it in V, it's just
Q delta V.
She just,
Oh.
she just took an
Because
AP
it's like
test.
1.6
I was
times
tired this
that.
morning and
Oh, I
I
use my
was
electron
like,
volts
sorry.
as the voltage.
No, that's the energy level.
They're energy drink.
Ah,
Ah, big
We don't
night.
even get these going.
Okay,
Yo, what?
So it's gonna
What are you
It's,
drinking?
it's just not.
I don't-
It's
I
like-
don't-
I'm digging the Princess
It's got,
Leia
like,
look, by the way.
Enough.
Actually, this
That's
is
good luck.
As in, like,
Should have worn that yesterday when it was made before. Yeah, missed that by a day.
or like
Oh. Had that chance.
Exactly.
Okay,
This
for
one.
the last time, I will ask you this question.
No. I was joking.
What?
Berg, you said you were going over all of them. You did not go over all of them.
Which other ones do you want me to go?
All of
About
them.
1 through 7,
Oh my God!
I don't
1,
get it, Berg.
4 through 9,
At this
51.
point, you might say
You
this.
can just go through.
Bro, with all due respect, what the hell is that? Nothing makes sense.
I need to do 5.
Hey, take me back to magnetism, bro.
I'd rather do
Whoa,
magnetism.
Let's do what I
Hey,
did.
basically,
Yes.
you know,
I thought you didn't talk about 4 through 6.
We went through all of it. You didn't go through 3, not 5, not 6.
I thought, but now I'm like, hey,
What?
I thought magnetism, but not anymore. Magnetism, not anymore.
Okay, listen.
Do you not?
Dude, I'd rather do like
You get it, right?
harmonic motion than this.
So, on 51,
It was boring.
okay?
It was boring.